This presentation will be about titration. We will define what titration is. We'll go over acid-base titration and redox titration, and then we'll do some examples. So we'll calculate molarity from a generic titration, we'll calculate molarity from a standard titration, and we'll calculate moles and mass from an unknown titration. Titration is a quantitative technique used to determine the concentration of an analyte. Quantitative meaning how much, analyte meaning thing we're studying. All titrations involve a chemical reaction, and you should therefore have a balanced chemical equation for them. Acid-base titrations use an acid-base reaction. Redox titrations use redox reactions. All titrations use a solution of known molarity, called a standard, to determine the concentration of the analyte. And here, finally, is some vocabulary. The titrant is the solution in the burette. The analyte or titrand is the solution in the flask. I favor using titrant and analyte because titrant and titrand sound ridiculously similar, and that's easy to get mixed up. Now, we have a picture over on the right there of an acid-base titration. You can see that it turned pink, and we know from doing lab that we want the lightest pink possible, so this person over-titrated a bit. Oops. So let's talk about how these things generally work when we do the experiment. Okay, so how does a titration experiment generally run? It follows this general form. A standard titration followed by calculating the molarity of the working standard, then an unknown titration followed by calculating the molarity of the unknown. At the endpoint of each titration, the moles of analyte is stoichiometrically equal to the moles of standard. And I use the word stoichiometrically here because it may not be a one-to-one ratio. So we have to use stoichiometry to get back and forth. All right, so why do we need to perform a standard titration? What is that about? Your titration solution is generally not perfectly stable, and it will degrade over time. It degrades over the course of weeks, but we need to know the concentration right now when we do our titration. So we use a primary standard to figure out the concentration right now. That's what the standard titration is about. Primary standards are incredibly stable and will give you reliable results, but they're often a pain to work with. In your redox titration lab, you used sodium oxalate as a primary standard, but in order to do that titration, you had to heat it up to a range of 60 to 80 degrees. Kind of a bit of a pain in the butt. You use your standard titration to determine the molarity of the working standard. In the case of the redox lab, it is potassium permanganate. Then you perform the titration on your unknown, and from that you can calculate the molarity of your unknown. So let's try some math, and we'll just start off with acid-base titration, and then we'll talk about that stuff from the lab. So we're going to ease our way in here and do a simpler calculation and build up to a more complicated one. You titrate 1.00 molar HCl into a 250 milliliter solution of NaOH with an unknown molarity and reach the endpoint at 22.85 milliliters. What is the concentration of NaOH? So we have 1 molar HCl, we use 22.85 milliliters of it. We have 250 milliliters of NaOH. And I'm going to draw a picture of what we've got going on here because, I don't know, it's not abundantly clear for me when I first started doing this, so I'm going to assume that it's not for you either. So we have our burette, and we're going into our Erlenmeyer flask. Okay, and I'm going to make our titrant, our HCl, purple, even though it is clearly not a purple liquid. I am just color coordinating here. And then I have green for NaOH. That's the stuff in the bottom. Okay, and so I'm saying I start out with 250.0 milliliters of NaOH. And I'm saying that I'm starting out with 1 molar HCl. And I use up 22.85. Okay, not the best 8, but hopefully we get the point. Okay, in order to do an acid-base or any titration, we have to start with a balanced chemical equation. So let's get ourselves a balanced chemical equation. So we're starting with HCl, and we're adding NaOH. We could write this the other way around, it wouldn't really matter. But we're making water because it's an acid-base reaction and a salt. Literal salt. Okay, now I'm going to put what I know underneath the thing I know about. So I've got 1 molar, 22.85. Okay, I don't know the molarity, but I know that my volume is 250 mils. Now, turns out this stuff doesn't matter for this type of problem. So here we go. Let's try to do these calculations. We first, when we're using stoichiometry, need to convert to moles. Molarity was moles per liter. So I'm going to put that up in the corner here. That equals moles over liters, because that is important for multiple parts of this problem. If we do 1.00 molar, that is the same as saying 1.00 moles HCl over liters. And if I multiply by that volume in liters, I will get moles. We'll pretend that looks like an 8. Now, we know that the amount of HCl is stoichiometrically equivalent to the amount of NaOH at the endpoint. So we can convert this into moles of NaOH. And it's a 1-to-1 ratio, so that's stupid easy. Because multiplying by 1 leaves us with the same number we started with. Okay, so now we've got that number, and we want to define molarity. So we take our 0.0285 moles of NaOH, and we put it over our volume of NaOH in liters. So that's going to be 0.250 liters. And we get a molarity hold on. I have to get down to my notes where the number is. 0.914, or sorry, 0.0914 molar NaOH. All right, we'll erase the accidental decimal point here. There we go. Now, why didn't I just use M1V1 equals M2V2? Because technically I could have been like 1 times 22.85 is equal to X times 250, and I get the same answer. No lie. Why can't I just do that? I am about to show you why not. Here we go. student titrates 25.00 milliliters of sulfuric acid with 35.02 milliliters of 1 molar solution of NaOH. What is the molarity of sulfuric acid? So again, we always want to start with a balanced chemical equation. So we have our H2SO4, and we're adding NaOH. And it's going to make water. Again, acid-base reaction always makes water. And a salt. But in this case, in order to in order to charge balance, you need 2 sodiums. So that means that you have to have 2 of these, and in order to balance it, we've got 2 of these. This is not a 1-to-1 ratio. That is important. It is not a 1-to-1 ratio. Okay, so we have 25.00 milliliters here. We don't know the molarity. We do know that we have 35.02 milliliters of 1 molar NaOH. Okay, and we don't need to worry about water. We don't need to worry about our sodium sulfate. We're going to do our math. We've got our 0.03502 liters, and we're going to multiply it by our molarity, which is moles per liter. And I can do this in either order because of the associative property of multiplication. It doesn't matter. Actually, I take it back. Commutative property. I can put it in whatever order I want. It's still fine. And I find that I have 0.03502 moles of NaOH. Okay, then I'm going to use my stoichiometry. For every 1 mole of for every 1 mole of sulfuric, okay, I have 2 moles of NaOH. And when I do that, I find that instead of 0.3502 moles, I now have 0.0175 moles, and I've rounded to the sig figs of my molarity, of H2SO4. Okay, and then we do the same thing that we did the last time, and we take that volume, or sorry, not the volume, we take that number of moles, and we put it over the volume, which our volume was 25. Oh, but wait, we have to put it into liters because molarity is in liters. And when we do that, and we put it in our calculators, we get 0.700 molar H2SO4. And I said I was going to prove to you that stoichiometry mattered in these problems, and I am about to do so. So if I did M1V1 equals M2V2, if I said 35.02 times 1 is equal to 25 times x, I would get 1.40 molar. Those two things are not equal. If you don't do the stoichiometry, you will get the wrong answer. So don't forget the stoichiometry step. And I will take off points if you use M1V1 equals M2V2, unless you explain 1-to-1 ratio, and then I'll let you get away with it. Here we go. All right, so let's shift gears here, and let's talk about our lab titration. I've put our titration setup, again, my amazing art skills. We've got permanganate as the titrant, we've got oxalate as our analyte. And in our lab notebooks, we've recorded a mass of oxalate and a volume of permanganate. And I will tell you right now, the volume of sodium oxalate solution does not matter. And you may be thinking, why does that not matter? It seems like it should matter. And here is the answer. We are worried about how many moles of oxalate we have, because we're going to use a mole-to-mole ratio to get back to the moles of permanganate. When you use a primary standard, and it's a solid, you're concerned with how many moles there are, not with the molarity. So here we go. Let's calculate the number of moles. We take our mass of sodium oxalate and we divide it by the molar mass of sodium oxalate to get 1.677 times 10 to the negative third moles of sodium oxalate. But our balanced chemical equation, that was a net ionic equation. So we need to figure out how many oxalate we have for every sodium oxalate. So we write a dissociation equation. We have done this, we are pros at it. And we note that we have 2 sodiums, but only 1 oxalate. So we have a 1-to-1 ratio between oxalate and sodium oxalate. If we do the math, we can write it out. It's the same thing, 1.677 times 10 to the negative third moles of oxalate. So now we did our titration. The number of moles of permanganate would be equal to the moles of oxalate at that end point. So that's what we're going to do in the next slide, the stoichiometry. All right, so in this point, we need our balanced chemical equation, and there it is. We have the data from the previous, and we want to go from oxalate to permanganate. So we have 5 oxalate for every 2 permanganate. And so we put that ratio in there, and we get 6.6707 times 10 to the negative third moles of permanganate. So now we have moles of permanganate, but we're not done, because we needed to calculate molarity. So first, let's go from moles of permanganate to moles of potassium permanganate, which is, yes, you guessed it, a 1-to-1 ratio. So we do our stoichiometry, we find out it's the same number of moles, and then we calculate the molarity. Molarity is in moles per liter. So we have 6.707 times 10 to the negative third moles of potassium permanganate, and we used 31.73, which we have to convert to liters, and we do, and we get a molarity of 0.02114 molar KMnO4. That is the molarity of our working standard potassium permanganate. Then you did another titration, so let's talk about that other titration. Okay, so part 2 of your experiment required you to find the concentration of the stock solution of peroxide and then figure out mass percent. So I'm going to draw the procedure involved so that I can keep track of where I am in my calculations, and I will label what I know about each part of the picture as I go. So currently I know the molarity of potassium permanganate from the first part of the lab. I know the milliliters that I used to titrate. I know the mass of the stock solution that I used, and I know the balanced chemical ratio. So what did I do to make this happen? I started with 10 milliliters of stock solution. I diluted it to 100 milliliters, and then I pulled out a 25 milliliter sample, which I titrated with the stuff I know about. All right, so let's figure out how many moles we've got of permanganate, because we need to know that to go on. So how many moles is that? We multiply molarity times milliliters. And we get 6.395 times 10 to the negative 4th moles of permanganate. How many moles of peroxide does that mean? I used up. So I take my balanced chemical equation ratio from here, my balanced chemical equation, it's 2 to 5, or rather in this case 5 to 2. I multiply it by 5, I divide by 2. So I started with 6.395 times 10 to the negative 4th moles of permanganate. And when I multiplied by 5 and divided by 2, I got 1.599 times 10 to the negative 3rd moles of peroxide. Okay, so now I know my moles of peroxide, and I can add that back in. But what I need is the grams of hydrogen peroxide in the diluted sample. We need the concentration. All right, so how do we calculate a concentration? We're going to do a conversion to grams. Use the molar mass. So we have 5.436 times 10 to the negative 2nd grams of H2O2 in 25 milliliters of that sample, because we titrated 25 mils. Okay, so we're going to take the mass of the peroxide, divide it by the milliliters of peroxide, and we're going to find the concentration of that peroxide. So that's 2.174 times 10 to the negative 3rd grams per milliliter peroxide in the dilute solution. The concentration of the sample that we took out and of the entire volumetric flask is the same. That is the definition of a homogeneous solution. So as a result, we know that the original solution is also 2.174 times 10 to the negative 3rd grams per milliliter. Now we need to use M1V1 equals M2V2 to get back to the original concentration. And here is where it can get slightly tricky. So we have the stock bottle. We took 10 milliliters from that stock bottle. So our V1 is going to be 10, and our M1 is unknown. Our V2 is the 100, because we want to know what we diluted the total amount to. So we set that up, and then we solve for M1, and we get 2.174 times 10 to the negative 2nd grams per milliliter. Now, our problem told us that we needed to have mass percent. We currently have a concentration. So we are going to have to get to the to the point where we can do the mass percent. So we're going to do that next. All right, now we had originally 9.3861 grams of peroxide. So we know the total mass. But what is the mass in the original sample? Well, we have our concentration, and we know that we used 10 milliliters of it. So if we multiply our concentration times the 10 mils we pulled out, we get that our original sample had 2.174 times 10 to the negative 1 grams of hydrogen peroxide. Mass percent is always part, in this case 2.174 times 10 to the negative 1 grams of hydrogen peroxide over the whole, 9.38361 grams, times 100. And when we do that, we find that we have a 2.210% hydrogen peroxide solution in the stock bottle. Hopefully you followed all of those gymnastics. Normally when we work in lab, we will have some kind of dilution step, and you'll have to do a little bit of M1V1 equals M2V2 action in order to make it work. So don't be shocked if that comes up in some problems. Just take it one bit at a time, and it helps if you draw out what you did, because you can figure out where you're going with things. So, summary. Titration is a quantitative technique used to determine the concentration of an analyte. Normally, you will go from a standard titration to calculate the molarity of your working standard, and then you'll use your working standard in an unknown titration, after which you can calculate the unknown molarity. Okay, molarity is always moles of solute over liters of solution. And make sure you use stoichiometry to go from moles of known stuff to moles of analyte. So you always need a balanced chemical equation for titration problems. If you don't set up a balanced chemical equation and you're doing a titration problem, you are doing it wrong. You must always, always have a balanced chemical equation. Okay, hopefully that all made sense and you're feeling confident and capable, but if you get stuck on it when you're going to do your lab, you can ask questions. I would be happy to answer them. If, however, you are just stuck on how to do stuff for the test, we will also try to answer those questions on Monday.